My name is Laura Peticolas, and I work at Sonoma State University with the Edion STEM Learning Team. I'm the Learning by Making project manager, and I'm presenting with my colleague, Professor Lynn Cominsky.
Hello, my name is Lynn Cominsky, and I'm a professor of physics and astronomy and director of the Edion STEM Learning Group at Sonoma State University in Northern California. And we are here to tell you about our Learning by Making curriculum, which is a year-long 9th grade integrated C-STEM curriculum that we have developed especially for rural high-needs schools.
Team members and teachers have enhanced our presentation by sharing their experiences with the curriculum through photographs, graphics, video, and video editing. Together, we aim to elaborate on the skills, practices, and concepts embedded in the curriculum to prepare students for a STEM vocation or career.
What is Learning by Making? Learning by Making is an integrated C-STEM year-long curriculum for 9th grade that implements all 3 strands of the next generation science standards. It focuses on scientific and engineering design practices and has been approved for at least the past 5 years as a pre-college requisite for the University of California or the California State University systems in Area D science. With LbyM, students follow a storyline that begins with a starter experiment, and then they design, construct, analyze, and explain their own experiments, measure and understand their own data that are personally relevant and critical to the future of our economy and our planet. LbyM has been positively evaluated for gains in science and math learning. We offer CTE connections through a yearly field trip and career presentations. And LbyM can serve as year 1 of 3 in an integrated NGSS pathway or as the CTE Energy Utility Track course.
The Learning by Making curriculum, or as we call it, LbyM curriculum, was designed with the 3 dimensions of science education in mind: scientific and engineering practices, cross-cutting concepts, and disciplinary core ideas. Most states have adopted science standards that originate from this report. For example, the next generation science standards, known as NGSS, were developed from this framework. The LbyM curriculum is grounded in scientific and engineering practices, which provides students experiences to do as scientists do. Students don't simply read about how science and engineering is done, but they gain real-life skills in these practices. They are actually doing science. For example, students make computer simulations, they communicate scientific and technical information, they develop and use models, they design, build, and refine technical devices, and they plan and conduct a variety of scientific investigations. The disciplinary core ideas in this curriculum focus on ideas in the physical and earth sciences.
Why is LbyM ideally suited for rural schools? Well, LbyM builds the skills that are needed for the modern workforce, including programming, troubleshooting, and electronics. It can satisfy either college entrance requirements or the CTE Energy Utility Track, all within a single classroom. LbyM was designed to deal with a mix of student abilities in the classroom. For example, we have double dare challenges for the speedier students. Since it's an integrated C-STEM course, only a general science credential may be needed in order to teach the course, and our focus is on environmental experiments using heat, light, soil moisture sensors, solar panels, etc., all of which relate to rural conditions. Now I'd like to share with you a few words from one of our teachers.
Hi, my name is Rohde, and I am a 9th grade science teacher at Roseland University Prep in Santa Rosa, California. What I love about teaching LbyM curriculum in my classroom is the hands-on component. It's really easy for the students to learn the interfacing of the web app, which I have behind me. It's really simple to integrate into a classroom. I'm able to see live what the students are doing, and they can work on it outside of the classroom. It's a great platform for students who are interested in learning basics on computer science.
Here is an overview of the LbyM curriculum. We have 3 units in which we're building skills. Unit 1, the sea turtle life cycle, introduces coding, and we actually do simulate a sea turtle life cycle. Unit 2 introduces wiring, digital multimeters, as well as wiring techniques and LED lights. Unit 3, we introduced the heat and temperature sensors that are the basis of most of our future experiments. Then we move into the experimental units in the spring semester, including water and soil, light and energy, and a unit that uses a mud-based fuel cell. In all of these units, students pose their own questions, engage in the entire NGSS cycle, including storylines. The main innovation for LbyM that's allowing us to do all of this work and to scale up our project in an affordable way is that we've developed an interface called the web app, which means we no longer need to provide custom computers to each student group. You can plug any computer into our basic board using a plain old USB cable, and you can take data through the Chrome browsers using the web app. So in Unit 1, the sea turtle life cycle, students are learning the basics of coding in the logo language, actually the turtle logo language, while they simulate the life cycle and environmental conditions for sea turtles. Now I'm going to show you a demonstration of the sea turtle web app. In Unit 2, students learn how to wire and control LEDs using the web app interface. So here's a picture of the board that the students have added the blue and the green LEDs to. They're not quite done because, if you might notice, they're missing their resistors. But the students can then talk to the microprocessor, the little Arduino clone that's on the board, as well as directly controlling each LED individually. In Unit 3, students learn how to wire and read data from our light and temperature sensors using the web app interface.
The Learning by Making curriculum provides many opportunities to build both students' technical skills while also supporting students' competencies in computational thinking. For example, students engage in computational thinking skills within the context of science when they implement and analyze data from an experiment about heat and temperature. Here on the slide, you see two temperature sensors being attached to a metal block and a wood block. Specifically, students must practice a category of computational thinking known as systems thinking when considering how to determine if a metal block is actually colder than a wooden block just because it feels colder, or rather, to determine it is not colder. In addition to systems thinking, as students determine how to calculate the accuracy of the temperature sensor readings, they practice computational problem solving, which is another category of computational thinking. The curriculum comes with video demonstrations of how to show students the steps needed to assemble electronic or scientific components used in the course. Next, we show an example of one of these videos demonstrating how to successfully attach the temperature sensor to a jumper cable, which we call a leash in the curriculum. On this slide, a student is holding a leashed temperature sensor. And now we'll listen to Arnold.
Hi, I'm Arnold Pelicano, and I teach at Palo Verde High School. In Unit 3.5, you're going to use your basic board, and this is how it was set up in Unit 3.4 with your optic sensor and your two temperature sensors. So the first thing that you're going to do is remove all three sensors and put them aside first. And then what you're going to do is you're going to get your leash. With the red wire on the left, you're going to put a 3-pin leg and stretch it to the other side. And again, with the red wire on the left, you're going to get your temperature sensor. With the flat side facing you, you're going to insert the 3 legs inside here.
Our first experimental unit is water and soil. We set up a pan with dirt in it, a drainage pan for the water that flows right through the dirt. This pan is tilted at an angle so that any runoff will collect in this basin below. The person who is demonstrating this is Jeffrey Rohde. So Jeffrey's pouring the water into the rain basin. It's dripping out onto the bare dirt, and you can see that a lot of the water is going right through into the collection pan. When he pours enough water in, you'll get runoff that includes a lot of dirt into the runoff pan. The next panel shows the setup when you put plants into the collection area over the dirt. And here's a little movie that's showing the rainwater dripping onto the collection area with the plants on it. Most of the water goes right through and very little runs off.
Hi, my name is Hoak. I teach Learning by Making at Big Bear High School. I love the water and soil unit because students get their hands dirty, literally. We start by talking about sweating and how it cools us down. Students aren't really sure how this works until we run the evaporation experiment with water and fans. This allows them to see for themselves how matter carries energy into and out of systems. We follow this by learning about the water cycle and how water flows through our environment and our lives. Once students are grounded in watersheds, it's time for mud. We build models of a watershed with aluminum clouds hanging above different soils and ground cover cascading into aquifer and runoff basins below. This is by far the students' favorite part. They love working with the elements, germinating seeds, and seeing the water flow through these systems. With this unit, students get a very deep and personal understanding of how water and the environment it is a part of affect each other. The three-dimensional nature of these experiments bring science to life.
For our light and energy unit, we start with a starter experiment called absorption, in which we have temperature sensors under black and white cloth and a hot light shining on them. And you can see the output from the web app. Temperature 0 is reading out from the black cloth, and temperature 1 is reading out from underneath the white cloth. And it's very clear that the black cloth has absorbed more light and has heated up the temperature sensor to a larger degree. We proceed through the light and energy unit to do experiments with solar cells. So here's a solar cell plugged into our basic board. And here's two different sets of output where you have the solar cell at an optimal angle for producing voltage, and then you turn the solar cell and get these lower voltage points when it's not at an optimal angle. And you can also see that similar effects happen to the current in this setup.
As teachers, we have traditionally sought to impart on our students what we refer to as content knowledge, or knowledge of basic scientific facts, concepts, and vocabulary. Building familiarity with and giving our students access to real science, just as it happens in the jobs they will be performing later in their lives, offers our students a head start. Learning by Making offers students the sustainable learning practices that they deserve, particularly in a rapidly changing world and workforce. As we have observed in the post-pandemic classroom, the curriculum continued to meet students' needs as their educational system was upended from underneath them. Because of these interruptions, we must meet their changes and perspectives with innovative ways of teaching not only math and science, but also problem solving and thinking. The grounding of this curriculum in the three dimensions of science learning empowers students to trust in their observations and their ideas. This is something that, unlike content knowledge, we cannot hand our students and tell them to learn. Curiosity and ingenuity must be fostered and practiced.
For more information on the Learning by Making project, please see our public files page at lbym.sonoma.edu. Watch our YouTube video. And if you're interested in adopting the LbyM curriculum, please write to me at the email shown on the slide. I'd like to thank contributions from all of our donors, as well as to the people on the Edion team. And a special thank you to Casey Lewiston on the Edion team for inventing the web app that is the major innovation that will allow us to go forward.